This is Lesson 1 in our Calculus 1 series, Functions. When one quantity depends on another, we can represent this relationship as a function. For example, if temperature depends on time, time is considered to be our independent variable because it does not depend on any other quantity, and then temperature is the dependent variable because it depends on time. So if we call temperature capital T and time little t, we can write capital T is equal to f of little t, saying temperature is a function of time. In general, we usually see x as our independent variable and y as our dependent variable, and we see y equals f of x, y is a function of x. Note that the defining characteristic of a function is that for each value of the independent variable, there is one and only one corresponding value for the dependent variable. So in the example above, for each time t, there is one and only one temperature capital T. And in general, for each x value, there is one and only one corresponding y value. We typically see functions represented in the following three ways. The most common way is algebraically. We're usually given a formula, y is a function of x. For example, y equals 2x squared plus 5x minus 3, or if we want to specify that this relationship is a function, instead of writing y, usually we see f of x is equal to 2x squared plus 5x minus 3. And so that's the algebraic notation for a function. We also see graphical notation for a function, and with graphs we're getting a visual representation of the relationship between x and y. Here we have the graph of a curve, which happens to be a parabola, and here we have a discrete set of points. We also could be given our function numerically by a table of data. So here's a list of the x values and their corresponding y values, or f of x values. With the algebraic representation, it's important to understand proper function evaluations. So let's take a look at this function f of x equals 2x squared minus 3x plus 6. And let's take a look at some function evaluations. The simplest one would be, for example, f of 0. Well, f of x is 2x squared minus 3x plus 6, so f of 0 is going to be 2 times 0 squared minus 3 times 0 plus 6. And so that simplifies to just 6. Similarly, f of 2 is going to be 2 times 2 squared minus 3 times 2 plus 6. So our 2 squared is 4 times 2 is 8, so this is 8 minus 6 plus 6, and this simplifies to 8. F of a would just be 2a squared minus 3a plus 6. But the evaluations do get a little bit harder than this, so let's take a look at f of x plus h. This is saying we want to replace all of these x's here by an x plus h. So we're going to have 2 times the quantity x plus h squared, 2 times the quantity x plus h squared, minus 3 times quantity x plus h, minus 3 times the quantity x plus h, plus 6. So we're here. And if we wanted to expand this to see if perhaps we could simplify anything, we would continue to expand like this. So x plus h quantity squared is x squared plus 2xh plus h squared. Don't forget we need to FOIL this out. Here we're distributing the negative 3, so we have negative 3x minus 3h, and then plus 6, and we could leave it like that. But of course it gets even harder than this, because typically what we see with calculus problems is the difference quotient f of x plus h minus f of x over h. So we just computed f of x plus h for this function. That's here. So let's plug this in for f of x plus h. And then we want to subtract from this f of x. So we definitely want to use parentheses here around our entire function f of x so that we're subtracting the entire function. And we have our h in the denominator. So the first thing we want to do is distribute this negative through here. So now we have a negative 2x squared plus 3x minus 6. And now notice that we have a positive 2x squared and a negative 2x squared. We have a negative 3x and a positive 3x. We have a plus 6 and a minus 6. And what's left in our numerator is 4xh plus 2h squared minus 3h. And our denominator still has an h. But now notice everything in the numerator has a factor of h, so we can pull out that h and cancel it with the denominator. So what we're left with in the numerator is then 4x plus 2h minus 3. And that's our solution here. Let's take a look at another difference quotient for the same function. We have here f of x minus f of a over x minus a. So here's f of x. Here's f of a. Again, we want to make sure to use parentheses here so that we subtract off the entire function and we get our signs correct here. So let's distribute this negative sign. So we have minus 2a squared plus 3a minus 6. And let's simplify our numerator. So we notice that we have a plus 6 and a minus 6 here. Now let's factor our numerator by recognizing that we can factor out a 2 from these two terms and a 3 from these two terms. So we have 2 times x squared minus a squared. And then let's factor a negative 3, leaving us with x minus a as the remaining factor there. And you'll see why this is helpful in just a minute. Let's continue to factor here. We have the difference of two squares. So this x squared minus a squared becomes x plus a, x minus a. And now we can factor even further with our x minus a and x minus a. So we factor out the x minus a, we're left with 2 times quantity x plus a minus 3. And we can cancel that factor of x minus a with the x minus a in our denominator, and our final solution is 2 times quantity x plus a minus 3. Again, these kind of difference quotients are important with calculus computations, and you'll see in later lessons why these are important. Now let's talk about the domain of a function. The domain of y equals f of x is the set of x values that we can plug into f of x. And the range of y equals f of x is a set of y values that come from f of x. So for example, f of x equals x squared, or we can write y equals x squared. That's our basic parabola. Our domain is a set of x values that we can plug into this function. Well, for this function, we can take any real value and plug it in for x. So our domain is all reals. We could also write this set as the interval from negative infinity to infinity. But let's think about our range. What kind of y values come out of this function? Our y values are the x values squared. So our y values are all the real numbers that are 0 or positive. So we can write that as the interval 0 to infinity closed on 0, meaning we're including y equals 0. More formal notation for the domain and range would look like the domain is a set of x values in the real numbers, and the range is a set of y values in the real numbers such that y is greater than or equal to 0. Now let's talk about some tips for finding the domain when we're given algebraic form. We want to look out for fractions because the denominator cannot equal 0, and we want to look out for even roots because what's under the even root must not be negative. And then I just want to mention here, in Calc 2, we also add to this list, we look out for logs. But that doesn't come up in this course because we're doing late transcendentals. So for example, f of x is equal to 1 over x plus 2. We know that x plus 2 cannot equal 0. So if we subtract 2 from both sides, that's saying x cannot equal negative 2. And so our domain is going to be the set of reals such that x is not equal to -2. And this is the more formal way to write it. And informally, we can just say x is not equal to -2. And we want to also look out for even roots because what is under the even root must not be negative. So for g of x equals radical 5 minus x, we know that 5 minus x must be greater than or equal to 0. So we add x to both sides, and this is saying that 5 must be greater than or equal to x, or x must be less or equal to 5. So our domain here is a set of x in the real numbers such that x is less or equal to 5. Or less formally, we can just say x is less or equal to 5, or in interval notation, we can say -infinity to 5 enclosed on 5, meaning we're including the 5 in our set. Let's take a look at h of x here. H of x is the fourth root of x plus 1 over x minus 1. So now we have an even root and a fraction. So we have two conditions here that our x values must satisfy in order to be in the domain. We need x such that x plus 1 is greater than or equal to 0. This condition is given by the numerator. And we need x minus 1 not equal to 0. And this condition is given by the denominator. So here, simplifying says that x must be greater than or equal to -1. And we also need, simplifying here, we get x is not equal to 1. So we need both of these conditions to hold for all of the x values in the domain. So we want the intersection of these two sets. Here's a set x greater than or equal to -1, and here's a set x not equal to 1. When we're intersecting sets of real numbers, it's usually easiest to use the number line notation to determine what our resulting set looks like. So here we have x greater than or equal to -1. That's saying we want x equals -1 and everything greater than that. So we start here. But we also need x to be not equal to 1. So that tells us that this point x equals 1 needs to be removed from our set. And this is our final solution set. So how can we write this in interval notation? This is the interval from -1 to 1. But notice it's closed on -1 and it's open on 1. Union the interval from 1 to infinity. Open on 1 here. And we always have the open parentheses on infinity. So this is our domain. Let's take a look here at f of x equals radical x squared plus x. Because we have an even root here, we know that we need what's under the radical to be greater than or equal to 0. So that means we need x squared plus x to be greater than or equal to 0. Factoring, that tells us we need x times x plus 1 to be greater than or equal to 0. Now notice that can happen in two ways. We need the product here to be greater than or equal to 0. So that means either both of these are going to be greater than or equal to 0, so x is greater than or equal to 0, and x plus 1 is greater than or equal to 0, or we could have both of these negative and still multiply to a positive. So we could also have x less or equal to 0 and x plus 1 less or equal to 0. That would also result in a product that is greater than or equal to 0. So these are the two cases that would give us a solution. Here, saying x is greater than or equal to 0 and x plus 1 is greater than or equal to 0, we simplify, and so we're saying x is greater than or equal to 0 and x is greater than or equal to -1. Okay, x is greater than or equal to 0 starts out with this solution set, and x greater than or equal to -1 looks like this. Now we need the intersection of these sets. We need the x values that have both of these properties. So our solution is going to be x greater than or equal to 0. Those are the points here that are colored by both the purple and the red sets. Here we have x less or equal to 0 and x less or equal to -1. And again, we're looking for the intersection of these sets. It's x less or equal to -1. So our final solution for the domain here is x in reals such that x is greater than or equal to 0 or x is less or equal to -1. We can put this complete domain on one number line and it looks like this. As a union of intervals, we could write it as -infinity to -1, union 0 to infinity. Or in set notation, we can write x is in reals such that x is greater than or equal to 0 or x is less or equal to -1. And that's our domain here. For functions given graphically or numerically, to find the domain, you want to find the set of x values that are shown, and to find the range, you want to find the set of y values that are shown. So for example, here, notice that the set of x values that are shown for this graph span from -2 to 2, including both endpoints. So that tells us our domain is going to be x's in the real numbers, such that -2 is less or equal to x is less or equal to 2. Or we could write that as an interval from -2 to 2 closed on both sides. And our range is a set of y values that are achieved by this graph. So we can see that that's going to be y is greater than or equal to 0 and less or equal to 4. So 0 is less or equal to y is less or equal to 4. As an interval, 0 to 4, closed on both sides. Now for this graph, we have a discrete set of data points. We want to be careful. Our domain is not going to be the interval from 0 to 6 because we're only talking about the specific whole numbers for which we have plotted points here. So our domain is the set of numbers 0, 1, 2, 3, 4, 5, and 6, because those are the x values for which this function exists. And the range is a set of y values that comes out of this function, so which y values are achieved by this graph? 0, 1, 1.5, 2, and 3. And that's our range. Similarly, for this table of data, the domain is going to be the list of x values, and the range is going to be the list of y values from this table. Note that when we are given a graph, we can check to see if it represents a function y equals f of x by using the vertical line test. And the vertical line test says that if the graph represents a function y equals f of x, any vertical line will intersect the graph at most once. So here, for this parabola, we notice that any vertical line will hit at most once. If we have x equals 2.5 as our vertical line, it's not going to hit the graph at all here, but that's okay. It says any vertical line will intersect the graph at most once. This ensures that for each x value, there's only one y value. And that's what we have here. So this graph represents a function. Here, however, we do have some vertical lines that hit the graph only once, but we definitely have vertical lines that hit the graph more than once. So because of this, this graph is not a function. Because we found one x value with 3 y values, and that violates the definition of y being a function of x. Now let's talk about piecewise functions. Sometimes we see functions given by a bracket, and then we have one function for these x values and another function for other x values. And because these are put together as one function, it's called a piecewise function. So the first thing I want to do is talk about how to evaluate piecewise functions. To evaluate a particular x value, we need to determine which part of the function to use. So for example, if we want to find f of 0, we have to figure out which function we're going to use here. Well, we take a look at our x value, x equals 0, and we realize that 0 is less or equal to 2. So 0 fits into this set, which means we should be using this function, 3 minus 1/2 x. So f of 0 is 3 minus 1/2 times 0, which is 3. Similarly, for f of 2, when x is equal to 2, that fits into this set, And so we're using the same function 3 minus 1/2 x. So f of 2 is 3 minus 1/2 times 2, which is 3 minus 1, which is 2. Now for f of 4, 4 is bigger than 2. 4 fits into this set of x values. Therefore, we're going to use 2x minus 5 as the function for f of 4. So f of 4 is equal to 2 times 4 minus 5. That's 8 minus 5, and that's equal to 3. And so this is how we're doing our function evaluations. You have to see for each particular x value which set it falls into, and therefore which corresponding function you should use. When we're talking about the domain of a piecewise function, we're talking about the union of the individual domains. So for example, here, we're saying this function is defined to be 3 minus 1/2 x for all of these values, then it is 2x minus 5 for all of these x values. So we're defining this function here for all of these x values. And so our domain is the collection of x's for which this function is defined. So we'll take the union of these sets, and in this case, the union of these sets is the entire real line. So for this function, we get all reals for our domain. Now to graph a piecewise function, we want to graph each part for its own domain. And then we put these on the same set of axes. So for example, we want to graph f of x equals 3 minus 1/2 x, but we only want to graph that for x less or equal to 2. So that's this line. And notice it has an arrow here because it's going off in this direction, but it stops at this point when x is equal to 2. And then for the other part of the function, we want to graph y equals 2x minus 5 for x greater than 2. So that's this line, and it goes off in this direction. But notice here, we have an open circle where x would equal 2. That's holding the place for the evaluation 2 times 2 minus 5. But notice x equals 2 is not included in this set, but all the values after 2 are included. So we're going to put an open circle at 2 comma negative 1 here. And so this is the graph of our piecewise function. Note that the absolute value function can be expressed as a piecewise function. We know that when we're taking the absolute value of a number, if that number is already positive, then the absolute value of that number is the same. If that number is negative, then we want the positive of that, so we negate it to make it positive. For example, absolute value of 2 is equal to 2 because 2 is greater than or equal to 0. Absolute value of negative 5 is equal to negative 5 because negative 5 is less than 0. So this is a formal way of defining the absolute value function, and this is going to come in handy for us in the future. And notice here, the graph of the absolute value function has on the left side, for x less than 0, has the function y equals negative x, that's this. And then on the right side, for x greater than or equal to 0, has y equals x. And together they make up y equals absolute value of x. Now let's talk about symmetry, in particular even and odd functions. F of x is said to be even if f of negative x is equal to f of x for all x in the domain. And f of x is said to be odd if f of negative x is equal to negative f of x for all x in the domain. So let's take a look at f of x equals x squared. Is f of x even, odd, or neither? Well, notice that in the definitions of even and odd functions, we're starting with f of negative x. So let's plug negative x into this function and simplify. F of negative x is a negative x quantity squared, which is negative x times negative x. The negatives will cancel, and this is equal to x squared, which is our original function f of x. So we've just shown that f of negative x is equal to f of x, and that's the definition of an even function. So this function is even. Let's take a look at f of x equals x to the third. Same question, is it even, odd, or neither? Again, we're going to start with f of negative x, and that's negative x quantity to the third, and that's negative x times negative x times negative x. Two of these negatives make a positive. We're still going to end up with a negative x to the third. And so this is negative of f of x. So we just showed that f of negative x is equal to negative f of x. That's the definition of an odd function. So this function is odd. Let's take a look at another. F of x equals x times the absolute value of x. Is it even, odd, or neither? Again, we start by plugging in negative x. And so here we have negative x times the absolute value of negative x. Well, we know that this negative sign doesn't have any effect inside the absolute value, so we can simplify by removing that. And so we have negative x times absolute value of x. And this is negative of the given function f of x. So here we have f of negative x is equal to negative f of x, and this function is also odd. Now let's take a look at f of x equals 1 plus 3x to the third minus x to the fifth. Same question, is it even, odd, or neither? Again, we start by plugging in negative x. So then we have 1 plus 3 times negative x quantity to the third minus negative x quantity to the fifth. Simplifying out, we realize that this is going to be 1 minus 3x to the third, and we'll get a negative sign that comes out here, so this will be plus x to the fifth. And notice this is not the original function f of x. It's also not negative of f of x, because we still have a positive 1 here. So f of x is neither odd nor even. The graphs of even functions have symmetry through the y-axis. For example, f of x is equal to x squared, or f of x equals absolute value of x are both even functions. And the symmetry is through the y-axis because what we're saying is that f of negative x is the same as f of x. So if you take any of your x values here and negate them, now you're over here, the f of x values are going to be the same. That gives you this reflection through the y-axis. Odd functions have symmetry through the origin, because now you're saying if you negate your x values, you then negate your y values. And so that'll give us symmetry through the origin. So here's y equals x to the third, and y equals x absolute x that we saw above. And also another example would be y equals sine x. And these are odd functions with symmetry through the origin. And with this, we'll conclude our lesson on functions.